Good morning, students. Welcome to Complex Analysis live lectures. In this class, we'll discuss mappings by elementary functions, how any regions or curves will be transformed under certain transformation. Okay. To start with, we'll have, yeah, just a second. So we'll start with a basic linear transformation. Under this linear transformation, we'll understand how a curve or a region will be mapped to. So start with linear transformation. So take W, which is equal to A times Z, where A is a non-zero complex number which is fixed, okay, complex number. Then where Z is of course in Z plane, a variable, non-zero variable, non-zero complex number. Now, what this a, because it is non-zero, so you can write a is equal to some a into e power I alpha, and z is equal to, it is again non-zero, we can write as r into e power I theta. So therefore, az is a r times e power I theta plus alpha. Okay, so this is z, this is z, then this is az. Okay, so you can see that radius, distance of this one from origin to z is r. Here distance is ar, okay, in w plane. Okay, and angle is, here we have theta and here we have theta plus alpha. Okay, so what we can understand here is that under this transformation, this points will be either, depending on what is ar will be smaller than r or bigger than r. That means it will be either expansion or contraction, followed by a rotation, because whatever theta is there, we are rotating by extra angle alpha. Okay, so therefore this one, we can see that this transformation az expands or contracts the radius and rotates this vector through an angle, extra angle alpha, about the origin. Okay, and so whatever we are doing here, we are making either that image, whatever region is there, whatever shape is there, that we are making either smaller or bigger, okay, without changing the shape, and we are rotating. That means this one, the geometry, they look similar. Okay, only thing is they may look smaller and rotated. Okay, that is the difference, or bigger and rotated, right? Also, if we consider linear, another one is this w is equal to z plus some scalar, fixed scalar which is complex number, like this. Okay, then easily one can see that here whatever shape is there, it is as it is, only thing is it is shifted, transformed. Okay, so that means the shape is same and even shape is not reduced, as it is. So you can call it this as a congruent. Okay, so this under this z plus b, the image shape and size, they are same, only thing is it is shifted from one place to the other place. Okay, same size, same shape, only it is translation. Okay, so therefore if you take any general linear transformation, w is equal to az plus b, where a and b are two non-zero fixed complex numbers, then this one, under this one, what are all we'll get? We get either contraction, okay, or expansion because of this one az. Okay, then plus b. So whatever we have, that one, that same shape will be shifted to translation. Okay, this followed by rotation. Then this entire shape whatever we are having, okay, this will have translation, means the position is moved, okay, different. Let's take quickly an example to understand what is this one. Is that, suppose take this, consider the map w is equal to 1 plus I times z plus 2. So our a is 1 plus I, okay, which is a complex number, b is equal to 2, again a complex number, right? Under this mapping, consider this rectangle, whatever we are having, this rectangle, what this first, this we, as I said, this we can split into two. First, this simple az, so that means I am denoting this capital Z as 1 plus I times Z, and then our actual mapping is Z plus 2. That's all, translation by 2. Now if you observe this 1 plus I times Z, here whatever we are having 1 plus I, that one we, the modulus of that is root 2. Okay, so and for Z if it is R, then it is root 2 times R. Okay, so whatever radius it has for this Z, radius in the sense magnitude, okay, then the new one whatever we are going to get here for this is the root 2 times R. Root 2 is 1.414, right? So therefore whatever shape we have, the shape will be bigger now. It is the contraction, not contraction, it is expansion. Okay, that's why we are getting this one, this bigger shape. So this is bigger than what we have here. That is clearly visible from this picture. And what is the angle this 1 plus I makes extra angle? It is pi by 4. So that alpha which rotates by pi by 4, that's why we are having here this degree is pi by 4. Okay, because 1 plus I, we are talking about this extra term which is 1 plus I, right? So that is pi by 4. So initially it was like this. So initially it was something like this. Okay, then it is rotated to pi by 4, angle pi by 4. Okay, so we will get this, right? That completes this one part, which is this one, Z. Okay, now what is remaining is this Z plus 2. That means it is translation. The shape is as it is. Okay, it doesn't rotate. Only thing is it shifts by everything by 2 units. So therefore what earlier it is origin, now that will be shifted to 2 units. Okay, so this B prime will be shifted to 2 units here, here and here. Okay, so finally this is our final transformation. W is equal to 1 plus I Z plus 2. Okay, so this rectangle shape is transformed to this one. Okay, that means what we have did, it has image has been enlarged and then rotated and then transformed. Okay, these three things happen. Fine. Now let's consider another interesting transformation. W is equal to this, W is equal to 1 by Z. Okay, and with this we will try to see what are all we can do it. Okay, when Z is non-zero, this W is equal to 1 by Z, how it look like? So if you call it this W is equal to U plus IV, okay, and Z is equal to X plus IY, then obviously one can check that this we can simplify. This W we can write this as 1 by Z, which is same as Z. I'll multiply and divide by Z bar, then Z into Z bar is Z square, absolute value, mod Z square. Okay, so this W is nothing but Z bar mod Z whole square. Okay, so how you can understand here is you take for Z, you take Z upon mod Z square. Okay, so it is just like, if you call it 1 by mod Z square is something like A. Okay, our A is 1 by mod Z square, right? Then when it is like, then it is Z by A times Z. Okay, then we are taking Z bar of that one. Okay, fine. Okay, now of course we can simplify this using this U plus IV, which is W, and Z bar is, this is U plus IV. Okay, and Z bar is X minus IY upon X square plus Y square. By comparing real part and imaginary part, what we get is U is equal to X upon X square plus Y square, and V is minus Y upon X square plus Y square. Okay, so under this transformation, this you can have what is our U and what is our V, right? Also we can do it in another way also. That means from here what we get is Z is same as 1 by W. Okay, then X plus IY is, you can get X value and Y value in terms of U value and V value, right? So we have a correspondence between this X plus XY and UV. Okay, so we have a result seeing that with this calculation one can check that the transformation W is equal to 1 by Z transforms circles and lines into circles and lines again. That means if we have a collection here, you have some circles, you have some lines, okay, then this will be mapped under this transformation w is equal to 1 by z to some lines and some circles. So it is not necessary that circle will go to circle, line will go to line. Depending on what we are taking, circle may sometime become a line, or line may become circle, or circle may go to circle itself, line may go to line itself. What we have is, what we can definitely say is that the collection of circles and straight lines will be mapped to circles and straight lines. Okay, fine. That is not a difficult one. Proof is obvious because you consider the general equation a times, okay, x square plus y square, a into x square plus y square plus bx plus cy plus d is equal to 0. This is the general representation. If a is not equal to 0, then it is a circle. Okay, if a is equal to 0, then it will be a line bx plus cy plus d, provided b square plus c square is greater than 4ad. Okay, so this b square plus c square greater than 4ad is required if it is a circle. That means a is not equal to 0, because we can complete this, we can try to write in the form of completing squares. X minus something whole square plus y minus something whole square is equal to, that means if you start writing something like x minus a whole square plus y minus b whole square is equal to some r square, then we get this condition that b square plus c square is greater than 4ad. Okay, fine. So if a is equal to 0, it is a line, and if a is not equal to 0 and b square plus c square is greater than 4ad, then this equation represents circle. Okay, now substituting x value and y value in terms of u and v, we get this. You simplify, substitute here, and if we simplify, what we get is that d into u square plus v square plus bu minus cv plus a is equal to 0. Okay, now this also is a either a line or it's a circle, just like how we have here, right? Fine. So that means it says that if d is not equal to 0, it is a circle, and if d is equal to 0, it is a line in w plane, right? W plane. We can have precisely the 4 cases. Suppose you take a is not equal to 0, then what we have earlier is a circle in z plane. Okay, this, if at all it not passing through the origin, that means if constant d is not equal to 0, so if we have a not equal to 0 and d not equal to 0, that constant, then what we get here is the circle under this one, circle will be mapped to this z plane is transformed into a circle not passing through the origin. So this will be mapped to, again, sorry, this is just assume that it is a circle. Okay, this map to circle again, because d is not equal to 0 and a is not equal to 0, this also doesn't pass through origin. Okay, and if at all a is not equal to 0 but d is equal to 0, that means if d is equal to 0, then we get a line equation. So therefore circle will be mapped to a some straight line equation. Okay, and that because a is not equal to 0, you can check that it is a line not passing through the origin, right? Now other two cases are if a is equal to 0 and d is not equal to 0, and if a is equal to 0 and d is equal to 0. So if a is equal to 0 and d is not equal to 0, therefore this is a circle but passes through origin. So if a is equal to 0, what we have here is a line. So a line not passing through the origin, this will map to a circle, but this time a is equal to 0, this passes through origin. So here some will, you will have origin, right? Similarly, if a is equal to 0 and d is equal to 0, so a is equal to 0 means we have a line, and d is equal to 0 means here also we have a line, right? So what we will get here is a line passing through origin, okay, maps to a line passing through origin here in z plane as well as in w plane. So these things we have written here clearly, one can go through it, right? Fine. Let's see one example to understand how this w is equal to 1 by z look like. So consider the line. So let's little bit increase this so that you can. Now it is visible clearly. Yes. So take this w is equal to 1 by z, okay, and consider the line x is equal to c1. X is equal to c1. For example, here this vertical line x is equal to c1. Two lines we have considered here. One is x is equal to c1. C1 is equal to minus half, okay, and c1 is equal to 1 by 3, okay. That means x is equal to minus half and x is equal to 1 by 3, okay. Then what can we say about? Similarly, we will discuss about horizontal line later, okay, this dotted line. So first take C1 vertical line, either C1 is equal to 1 by 3 or minus half. We will just taken two examples, because if it is on right hand positive side, what we will get, and if it is a negative side, how we will get, right? Because x is equal to C1, okay, x is equal to C1, where C1 is not equal to 0, that means it is a line not passing through the origin, okay. So what it will be mapped to, from previous one, if we have a line, okay, not passing through the origin, then it is transformed to a, here this one you can check, then it is transformed to a circle passing through the origin in w plane. So what is that one? Because one can write that equation as, if you simplify this, u minus 2c1 whole square plus v square, which is equal to 1 by 2c1 whole square. This is the circle equation, which is here. C1 is equal to 1 by 3. So this one, whatever we are writing here, this is the circle passing through the origin, okay, and centered at this, whatever here we are having, 1 by 2c1. This value is 1 by 2c1, and radius is also 1 by 2c1, okay, right? Similarly, if you take c1 is equal to minus half, so c1 is equal to minus half, so therefore this is this side, left hand side you will have with center 1 by 2c1, so you take whatever it is there, right, and in this side, right? So any line x1, so call it x is equal to c1. If c1 is greater than 0, it will be this side, okay, passing through the origin. If our c1 is less than 0, then it will be left hand side, okay, again passing through the origin, right? Similarly, if we take vertical line y is equal to c2, that means this one. If we consider these vertical lines here, or here one is above the x-axis and the other one is below the x-axis, right? Then also we can check that this time again it is a line not passing through the origin, so therefore whatever we are going to get, it is a circle passing through the origin. So what we are getting here is this one, this c2 for minus, okay, and for c2 is equal to half, you will get this one, okay. So these are basic easy calculations. You just substitute those values and see what we will get there, right? So under the transformation w is equal to 1 by z, a vertical line is translated to circle, okay. Similarly, horizontal line is also transformed to circle, okay. Yeah, let's make it this smaller, or even if we leave it, it's not able. Okay, so now so whatever we have seen so far is something like we have seen az plus b, okay, the transformation, which is linear transformation, and second one what we have seen is w is equal to 1 by z, okay. Now what we'll see is more combination of these two, which is linear fractional transformation. That means w is equal to some az plus b upon cz plus d, okay. So if our z is equal to 0, c is equal to 0, then what we have is precisely this first case, okay. So this whatever we are having, if c is equal to 0, this will become this if c is equal to 0, and this become here if we want something like 1 by z, right? So some cases it is just like when we have say a is equal to 0, then we can write it in this form, say suppose a is equal to 0, just look like this, even though it is not of same, but it is a cz plus d of that kind, or you take d is equal to 0, then c is equal to 1, it is a special case, okay. Fine. So you can have c is equal to 1 and d is equal to 0. Under this case you will get, So this W is equal to AZ plus B upon CZ plus D, which is more generalized than what we have seen here. Okay, and that is called linear fractional transformation, or it is also called Mobius transformation. Because why it is called linear fractional? Whatever we are having in this numerator, it is a linear transformation, and whatever we are having in denominator is also linear transformation. And also sometimes it is called as bilinear transformation, because it is linear in W as well as it is linear in Z. Okay, it is linear in both, right? Because we can see that this W we can write as A upon C plus BC minus AD by C into 1 by CZ plus D. Okay, so you can write this as W is equal to A by C plus, so that means you can write this as A by C plus this constant. Okay, you might have, we can write it as something, then W. Okay, where this W, suppose this W is nothing but 1 by Z, where again Z is nothing but C times small z plus D. Okay, so basically what we have seen is that these two, so using these two we got this one. Okay, so under this linear fractional transformation also, whatever circles and lines will be mapped to circles and lines because of this setup. Whatever we are having, this W is equal to some scalar plus scalar times W, where W is equal to 1 by Z. Okay, and we have just now seen 1 by under 1 by Z, circles and straight lines are mapped to circles and straight lines. Okay, and this Z, whichever we call it, this CZ plus D. Okay, fine. This W is equal to 1 by Z. Okay, and Z is equal to CZ plus. That means this we are calling it as W, and this below one we are calling it as Z, right? So we can see that this linear fractional transformation also transforms circles and lines into circles and lines. Okay, fine. Now we can extend this linear fractional transformation to the extended complex plane. That means we can define the value of this function at z is equal to point at infinity. Okay, so t of z, we can define t of z is equal to az plus b by cz plus d. Okay, so if I let me write here, so t of z is equal to az plus b by cz plus d. Of course, what condition we require is ad minus bc is not equal to 0. Okay, and this, what can you say about t of infinity? How we can define so that this t will become continuous? Okay, so this t, suppose assume that c is equal to 0. If c is equal to 0, then it is just like az plus b, or a prime z plus b. Okay, so as z tending to infinity, we know that this also tends to infinity. So this equal to infinity if c is equal to 0. I repeat again, if c is equal to 0, we don't have any denominator here. It is of just like a prime z plus b prime. Okay, so as z tending to infinity, this right hand side also tends to infinity. So t of infinity should be infinity if c is equal to 0. Okay, now if c is not equal to 0, if c is not equal to 0, then what can we say about this t of infinity value? That means if c is not equal to 0, then this value is a by c. Why? You can take out z common both sides here, numerator as well as denominator. Then it is a plus b by z upon c plus d by z. So as z tending to infinity, b by z tends to 0 as well as d by z tends to 0. So what is remaining is a by c. Okay. Now we can also have, when this t of what value is equal to infinity, if c is not equal to 0, because if c is equal to 0, then t of infinity goes to infinity. Okay, so if again c is not equal to 0, what z will map to infinity is the question, right? That means what we require here is, this side we want infinity, so what z we can substitute here so that we get this infinity. Okay, that is basically true here. If z is equal to, if you take this cz plus d, this denominator if it tends to 0, then this side, and of course if az plus b, that is non-zero, and cz plus d tends to 0, then we are done. So therefore t of minus d upon c, that's why we have taken c not equal to 0, at this point this is equal to infinity. Okay, so t under this map, infinity goes to infinity and minus d by c goes to infinity, and infinity goes to a by c if c is not equal to 0, right? So you can check that this under this, with this definition, this t will become continuous, okay, in the extended complex plane, right? And of course you can check that this map is bisective with inverse exists. Therefore t inverse also we can define from here. T inverse has these properties, which is minus dw plus b by cw minus a, and you can define what is this t inverse. From these two we can define what is t inverse of infinity, t inverse of a by c, t inverse of infinity if c is not equal to 0 and c is equal to 0, okay? And this is very basic result. You can easily prove it that if t1 and t2 are s and c, suppose s compose t, if s is a bilinear transformation and t is a bilinear transformation, then their composition s compose t is also a bilinear transformation, okay? Whether I use the word bilinear transformation or linear fractional transformation, both are same, right? This proof even I no need to explain. You can use the fact that write tz and sz in this fractional linear form with this coefficient satisfying these conditions, then find the composition and substitute it, and you will see that you will get it again in that same standard form, okay? So therefore it is also a linear fractional transformation. So those calculations I skip. It is not at all, I mean, one can easily solve those problems. It is not a difficult one. You can check that here this coefficient is non-zero, satisfying those conditions. So therefore, it is also a linear transformation, linear fractional transformation. Fine. Now, what is another result about linear fractional transformation is that it can have at most two fixed points. What is meant by saying fixed point? A z0 is said to be a fixed point if that point under that transformation map to same point. T of z0 is equal to z0, then we say that z0 is a fixed point, okay? So with respect to this, what you can see that every fractional linear transformation, only maximum 2 points can be sent to itself. That means they can have, every linear fractional transformation can have at most 2 fixed points in the extended plane, okay? So that is again very easy. Just simply solve this t of z0 is equal to z0 and you will get a quadratic equation, okay? Not exactly quadratic equation. It is depending on whether this c is 0 or not. If c is non-zero, then it is a quadratic equation, so it will have 2 roots, okay? If c is equal to 0, then you have a linear equation which have a 1 root, right? So in any case, it will have the maximum possibilities for this z0 is 2. So that's why any linear fractional transformation can have at most 2 fixed points, right? Fine. Now, how one can find a linear this fractional linear transformation sending some given 3 points to another 3 points, okay? So for that we have an implicit form, that means explicit formula, that w minus w1. So you have z1, z2 and z3 in z plane, okay? These 3 points will be mapped to w1, w2 and w3. So what is that t satisfying? So that t satisfies this equation, which is w minus w1 to w2 minus w3. So you can say 1 2 3 like, okay? Then w minus w3, w2 minus w1. So 3 2 1 is equal to z minus z1 into z2 minus z3 upon z minus z3 into z2 minus z1. One may see, you can easily verify this. How one can verify that a linear fractional transformation satisfies this? You simply cross multiply and bring it one left hand side, one values. That means this part, just simply cross multiply, okay? And substitute when z is equal to z1. When z is why after cross multiplying we have to substitute, because here in denominator you may get somewhere 0 and so on. So z is equal to z1, then whatever you substitute, what is remaining is w is equal to w1. That means z1 will be mapped to w1. Similarly, z2 will be mapped to w2. z3 will be mapped to w3. So t will have this one. The required linear fractional transformation will satisfy this condition, right? Fine. Now, if one of these zi's, see, suppose that means this t is defined an extended complex plane. So if one of these zi's says z1, for example, z1 is infinity, then we know that by taking this z1 common outside, what you will see here is that the required transformation is obtained by simply deleting the factors involving z1, because simply z1 take out here and take out z1 here. Okay, the z1 will get cancelled. Here z upon z1, z2 upon z1 will be there. Okay, so those two terms will be go to 0, so they will 1 minus 1 minus, so okay, those two terms disappear, right? So what I mean to say is that if z1 is infinity, then in this, wherever z minus z1 term is there, those things we can remove them. Okay, and remaining is the required transformation. Let's see quickly one example how one can find. Suppose we want to find a linear fractional transformation that maps z1 which is equal to minus 1 to w1 which is equal to minus I, and we want to send z2 is 0 to w2 which is 1 and z3 which is equal to 1. That means we want to have a linear fractional transformation which sends minus 1 to minus I, 0 to 1 and 1 to w3 which is I. How we can find? By simply using this, by simplifying this required transformation, w minus w1 into w1 minus w3 upon w minus w3 into w2 minus w1. This is a basic calculation, and substitute. It is simply just substituting and calculating, that's all. Okay, substitute the values of w1, w2, w3 here, and substitute the values of z1, z2, z3 here. Okay, in right hand side you have z, and left hand side you have w. So what you get is it involves w's as well as z, and try to bring w one side and other things on the other side. So what you will get here is w, which is the required transformation, I minus z upon I plus z. Okay, if see, suppose if you have z is equal to 0, so when you substitute z is equal to 0 here, I upon I which is 1. Okay, we are done. When z is equal to minus 1, it is same as I plus 1 upon I minus 1, right? You can multiply by I minus I plus 1 by I plus 1. Okay, then it is I square minus 1, which is I square is minus 1 minus 1 minus 2 you will have, and you simplify this, and what you will see is that you will get minus. Okay, so it is not at all difficult one, and one can find this, right? These are some of the one can see just one example which involves infinite. So we want to send 1 0 minus 1 to I infinity and 1. Okay, because w2 is equal to infinity is involved, so we can eliminate the words which contains w2. So that is this very it is not at all difficult. Why you want to remove that is w1 minus w minus w1, w2 minus w3 upon w minus w3 into w2 minus w1. So here we want w, we know here w2 is infinity, right? So if you take w2 outside, if I take w2 common, so what we have here is w into w minus 1. So this is 1 minus w2 upon w3, sorry, w3 upon w2. Okay, w3 upon w2. Similarly, in numerator, if we consider denominator, sorry, so w minus w3 into w2, if I take common, then 1 minus w1 by w2. Okay, so as w10 tends to 0, this value tends to 0, this value tends to 0, w2 will get cancelled. So what is remaining is w minus w1 upon w minus w3 as w2 tends to infinity, or the value of w2 is infinity. Okay, so therefore that's why that linear transformation, left hand side you have only this, and right hand side we have all these three terms. Simplify and you will get this. Okay, that simplification and all you can do on your own. It is not a difficult one, right? So you can take some exercise. In next class, what we'll see, maybe that may be the last class for this complex analysis course. So in next class, what we'll see, another interesting mappings. One is we will try to see what is the linear transformation. So we will find a T which maps this upper half plane, okay, to unit circle. I'm just writing overview. Okay, in details we'll see next class. And second one, we'll talk about if sine z. Okay, that means w is equal to sine z under this transformation, how the any given curve and all how they map to. Okay, and also we'll see this w is equal to z square and z power half, which are this is a multi valued function, so branches will be there under this functions. Okay, uh, how something will be mapped to the how if you take something in z plane, how it will be mapped to w plane and so on. We'll see these things, and I think with that our complex analysis syllabus is completely discussed. Okay, we'll stop here and we'll see one more last lecture. Okay, thank you.